A very good evening, everyone. It gives me immense pleasure to welcome you all to the day 4 of our 1 week online faculty development program on advanced computing and its application trends, organized by Department of Computer Science, Parvataneni Brahmaya Siddhartha College of Arts and Science. Now, I would like to invite Harshita Reddy, Assistant Professor, Department of Computer Science, to give an introduction about our session speaker. Over to you, Harshita.
I'm not sure if she's speaking. We couldn't hear anything.
Yes, sir. Just a minute. I'll let her.
It's okay.
Arishita, are you there in the meet? Sir, she can unmute herself, sir. I had made her as a co-host. She can unmute her. Yeah, sorry for the delay, sir. Now I would like to take the privilege of introducing our session speaker, Mr. Sivakishore Vadugu. Mr. Sivakishore Vadugu, an accomplished IT professional with over 17 years of rich experience in the areas of data warehousing, ETL, cloud technologies, and technical architecture. Mr. Sivakishore was born on March 23rd, 1984 in Vijayawada. He completed his Master of Computer Applications with distinction from Acharya Nagarjuna University, securing an outstanding 92%. Prior to that, he earned his bachelor's degree in computer science with 87%. His professional journey began in India as a software engineer, where he worked extensively on Informatica-based ETL development, test tuning, and data warehouse projects. Over the years, his career progressed across various domains, including banking and automobiles, taking him from India to Germany. Currently, he is working as a senior technical architect in Frankfurt, Germany, where he is responsible for designing and managing large scale integration systems for one of the world's leading automobile manufacturers. His role involves ensuring stable integration environments, managing teams, synchronizing marketing data, and implementing projects using the SAF, the Safe Agile methodology. Previously, he made significant contributions as a technical architect in application management services, where he played a key role in vendor transactions, capacity, and availability management. Mr. Sivakishore's technical expertise spans a wide range of platforms, including Informatica, Oracle, Apex, SQL, Unix shell scripting, Control M scheduling, Power BI, and AWS cloud services. He is also ITIL certified and well versed in ITSM tools and processes. In addition to his technical depth, he is admired for his leadership, communication, and mentoring skills. Beyond his professional life, Mr. Sivakishore is passionate about singing, cooking, and event management, reflecting his creative and enthusiastic personality. We hardly welcome you to the today's session, Sivakishore sir.
Thank you so much, sir, for the
Yeah,
crisp
you,
introduction.
you
I'm
yes, sir.
very
You
glad.
can take over the session, sir.
Thank you. Thank you so
Thank
much.
you.
Yes. Hi, everybody. As you have heard, yeah, almost a lot about myself. Even I also very, happy to hear about myself. And yeah, hope you guys have a good day. I already know that it's almost evening in India. I'm definitely sure that it'll not be a, not a boring session, I would say. Sorry to use that word. Let's try to make interactive session if you feel like if you wanted to communicate with me, you can raise your hand or maybe you can post your question on the chat. I'll try to give a pause in between. I don't have so many slides or so much of data to go through, but I try to help you out in understanding today's topic, which we had to talk about. Let me quickly share my screen and then give a quick glance of what we will talk today about. Yeah, can somebody quickly raise your hand and then say it's visible? I hope it is visible. That's what I also see myself.
Yes, it's visible, sir.
Thank you, sir. Thank you so much. Yeah. As I mean, I'm pretty sure that you're not a just college entry person or somebody who's doing masters or something else. You already know much about the programming models and etc. etc. But still, maybe in today's session, we try to discuss together and try to learn something new, which maybe you know more or maybe I know more. We try to make it little mixed session together. As I said, if you wanted to talk, you can raise your hand. I'll try to respond to your questions. If the question or if I can give the answer right away without disturbing the session, I will try to give it right away. If not, I will park the question. I'll try to give that answer to the organizers. Maybe later you will get the answers directly to you. Okay, hope that is fine. I'll also go off on my camera, not to distract myself looking at myself. Please, I will just go over the audio only. Just give me a minute. Okay, good. So let me quickly, as already introduction has been over, I can't give too much of introduction about myself. But as I already prepared myself a quick slide about me, I would like to show here. Yeah, I did my master's in computers and sciences, or MCA in PBC College of Arts and Science, and I did my bachelor's degree also from the same college. I'm so proud, even now. Yeah, I'm working, and immediately after my college, I've joined in Wipro, worked for a couple of years, and then moved on to HCL, worked for there for like around 4 years, and then I've got an opportunity to come to on-site. I'm right now in Germany, Frankfurt. It's one of the largest automobile industry or the country, I would say. If you name some of the companies like Volkswagen, Audi, Fiat, Skoda, Porsche, BMW, Mercedes, all these are from Germany brands. Yeah, there are so many other which I couldn't really recollect and then give you the names. But yeah, right now, I mean, I had worked with Deutsche Bank for almost 6+ years in asset management, and afterwards I moved on to automobile, where I worked with Volkswagen for almost 8 years, and then now I'm working with Mercedes. Yeah, both are automobile industries only. Mostly, what I have learned is on the methodologies and architectural side. From the beginning, I wasn't completely on technical side, and then later on moved on to architectural, technology architect as a technology architect. Mm, yeah, right now I do work on the area of data and analytics. Analytics is little part of my daily life, but most of the time I'll be working on data and reporting tools and integration and yeah, all the stuff. So it's been almost 17 years since I passed out of my college, almost, and yeah, that's what my career or experience is. I was born in India, but right now I'm staying in Germany. Yeah, and these are the languages which I know, including computer, some of the computer languages. Yeah. Uh, Sir already told about so many, what do you call, hobbies I have, but yeah, over the period of time, they all left. I just left with few of the things like experimental cooking and event management. Anyways, that's quickly about myself. Let's move on to the today's topic and agenda. Okay, so why are we here? You know, and how much time you're going to be here. You already know. As I said, like it's late in the evening. I don't try to make it a little boring. And thank you so much for PPC Tata College of Arts and Science resources and Ravikiran sir for giving me this opportunity to sit with you guys and then try to talk about parallel programming models and maybe as I said, like we try to learn together. That's what I feel like. It's not like okay, somebody give a session and then we just listen to it. No, I just wanted to make it a little interactive so that it will be fun for you as well as some learning for me. Anyways, so that's what we are gonna learn or talk about in today's session. Okay, let me quickly move on to the yeah. If you talk about parallel programming models, one can say from when the programming started in general. Any guess? Somebody can type in also. I'll just follow the chat. When do you think the programmings are started or anything? I think. Okay. So it's mainly, this innovations in parallel programming was started in 1950s. That time they were talking about computers and etc etc etc, but not into a deep parallel programming. They do have, but late in 90s, 60s, and 70s, with the advancements like supercomputers, and afterwards in 1980s, like clustered programming, all these things, there is a lot of advancement in parallel programming. Obviously, I mean, even now also you might be doing. I'm pretty sure that we'll be doing two things at a time, almost parallel processing. That's what we are doing in our daily life. The same thing, the same advancements are happened on computer sciences also. And in early 2000s, there is a specialized hardwares like GPUs are invented, which further drove innovations, making parallel programming a mainstream task by bringing it to desktop computers. Maybe in the 1950s, as I said, it's just the beginning. In 1960s and 70s, it's just the supercomputers and vectorization of the computers and blah 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 came up. And 1980s, cluster computing and conferences. And in 2000 and afterwards, even now also, we are just talking about GPUs and everything. So this is the very basic of when the parallel computing was started. Okay. Yeah, I would appreciate if some gestures was given, like understood or thumbs up or something like that. It'll be interactive. That's what I mean to say. Anyways, I will move on. Yeah, good. Let's see. Why we wanted to get into parallel programming? Just think about your regular life itself, or regular work itself. Let's say if I am the only one who is working on a particular topic, I might consider me as a thread. I'm a thread. I'm working on everything. I'm trying to write the code. I try to read the data. I try to do something else, or bookkeeping and etc. 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 That's the very traditional way of working. But let's say I have managed to recruit one fresher who can work for me on bookkeeping or account keeping. Done. On a same day, we both are working together, and then we can make some work better and faster, isn't it? And also, I mean, we just wanted to come out of the regular way, or the normal way of working on the tasks, and make it literally fast, which made inventions in parallel computing and parallel programming, where we are right now in. Just consider an example of, okay, but I mean, I'll just take a step back. So why we have to shift from regular processing to parallel programming? It's because of high costs incurred. So as we were talking about the same example, only I am the one who is working. So I may be working for 10 hours, but I may not be able to fully finish my task within the given time. The reason is I'm the only one single-handed. I have to work on many other tasks, which is quite not be possible. That's the reason I have got another hand, working hand, means I have doubled the resources, and I'm able to deliver it faster. And yeah, when you talk about cost, when compared to the what do you call the work or the deliverables, it's really negligible. So that is where the first shift where it has come from is the cost, the high cost incurred on programming, I mean, parallel computing. It limited us to come back to the parallelism. So when we talk about reasons for the shift, power and heat limitations, also performance gains, parallelism, as well as cost and space efficiency brought us to get into the parallel programming or parallel programming models. I mean, if you look at the screen, the bottom screen, okay, quickly take a 10, yeah, is a pointer. So if you look at this diagram or chart, so until 2000s, around until 2000s, we are working on single core computing. I mean, this is a core compute cores count, and the other one is the I think it's the processing speed. If you look at until 2000s, almost we are working on a single course. These are the core numbers, 1, 2, and doubling it. Sorry, actually it's blended out. So until 2000s, the work delivered is literally slow. As soon as we started increasing the cores, the time taken to finish the activities is being reduced drastically, which are the advancements in computers, and that is the parallel programming brought us to us. So if we talk about how does it work, how it works, so we just, as we have looked at here, a single thread working on multiple processes may take a lot of time, whereas in I've introduced multiple threads like threaded applications or operating system scheduling, as well as parallel or sequential processing. All these are the things which are behind the uh, parallel programming. As well as we have some challenges also in regular computing systems, like software design, programming complexities, migration of legacy codes to move from legacy systems to the other uh, advanced systems. All these things are the limitations for us, and which has challenged us to move from limited programming, or single threaded program, to a multi-threaded programming, or I would say parallel programming. Okay, and you may be wondering why we have these tankers doing here. I'm pretty sure that you might be knowing the data centers of most of the large companies. They are almost under the sea. I would say, yeah, under the sea, or maybe in a cool area where the systems are kept in, because it consumes a lot of power and produces a lot of heat. So to prevent them, they just keep them under the sea. I think Microsoft and Google, they also have under the sea data centers. But yeah, let's say if we wanted to, if we went parallel, because of the limitations of the sequential processing, as well as preliminary the stagnating performances of single core processes. As we see here, the stagnation was there because of the single core, and as soon as we started introducing multiple cores, we are able to get the better performance. These are the main reasons from shifting towards parallel computing. Are you with me? Yeah, I would assume. But yeah, so these are the very beginning, and if I would say, these are the challenges what we have related to the parallel computing, as well as why we are moving towards parallel computing. Let's move on and quickly to the other slide, where maybe I will be talking about the challenges what we have in traditional method. The first challenge which we can think of is communication. So consider I have what do you call? We can say communication overhead. So let's say, as I said, a single person is working on. So he has to think about multiple things at the same time, may not be able to process the data, or process the system. So to that's the main basics of the programming. Obviously, one will be, one processor may be talking to another processes, or maybe a file sharing, or maybe a message queue, or something else. So all these are the regular things which will happen when a program is running, for sure, right? So we have a communication overheads, like time and resources spent on the data exchange. Latency means the delivery of the messages and etc. Synchronization issues, as well as the second one is the synchronization issues, where we can see the processes are not working well together. Let's take the lines. Yeah. So where I was, sorry. So we are talking about synchronization issues and latency. So in synchronization, as I was mentioning, the processes work together correctly, but there could be a problem that the synchronization may not happen at a time for two processes, and it might bring to a issue. And also when we're talking about load balancing, the variability of workloads and execution times, which make predicting tasks, while working on, might be difficult. It might make the things difficult. So all these things are brought up together, which could be the evaluation of the parallel programming. The main reason for the parallel programming is to make the processing better and do the programming models better way. I hope you guys are with me. Okay. Can you think on maybe which are the challenges do you think is there or most difficult for new parallel programmers, I would say? A quick question, like, which of these challenges do you think is the most difficult for new parallel programmers? Maybe a communication, synchronization, load balancing, or the debugging. I mean, just think about debugging also. It's really hard for any engines to perform the debugging, which will consume too much of energy and power, and may not be able to deliver the accurate results within stipulated time. And that also make us to think about towards parallel programming. Yeah, I hope you guys are with me. Thank you. Let's move on. So what are the parallel programs that we have? So we do have a couple of parallel programmings, and also maybe in upcoming slides it will just explain us which programming model we have to pick up, or can be considered for your programming. So a programming model is a conceptual framework and set of rules that, as you already know, that guides how a developer thinks about organizing and solve the problems with help of code. Also defining the relationship between the different parts of a program, just like functions and order of execution. Like, as you know, in maybe in C, C++, maybe I'm talking about older languages, in Java or something else. So all these are having a main program which will re-trigger some of the individual functions, communicate to each and every function, and forward the variables, and get the return values and etc. So this is a typical programming model which you're already aware of. So to execute a better program better way, so it serves a high level abstraction, providing a blueprint for creating the software that works with a specific environment, such as hardware platforms or cloud services, and etc etc. And also which will help you in performing the problem, or providing that solution for that particular issue within a better times. Yeah, for examples including the imperative programming, functional programming, and object oriented programming, each offering different approaches to solve a problem. The key aspects for the programming models are conceptual framework, abstraction, structure, and guidelines. As I was talking about, just talk about a C program where I just wanted to add two variables. I can do in multiple ways. I can simply write it in, a plus b is equal to c. I mean, c is equal to a plus b, print c. That's a very simple way. But instead of writing that way, we can also create a function which can take two variables and return sum of it, and I can call it, or maybe reusable programming or reusable functions. So all these are the aspects, or conceptual frameworks that we have to come with and write it in a structured way with a proper guidelines given. Okay, so whenever we talking about any computation, anything, we will have data sharing, or yeah, you just talk about C programming itself. So it can also share the variables between one function to another function and return some values. Means we are communicating with each and every thread, as well as we are sharing some data in between. So when we talk about this sharing, I'm just talking about a very plain model. But when I talk about any application, let's say customer relationship management application, which will be shared across multiple users, all they will be logging in to the platform at a time, and they try to fetch the user information. Let's say I'm a car dealer and I wanted to access the main database of Mercedes. And I'm talking about only one dealer. Likewise, on a same city, multiple dealers might be logging into the system, and they wanted to fetch the data of a single user. Maybe it can be a single user or maybe multiple users. And because they wanted to have the sales performed. So they are trying to access the same memory multiple times, or I would say multiple. I don't say multiple times, but they try to access the data. It can be a same data or maybe a different data sets. Fine. So when we talk about this communication processing or threading or data sharing, it introduces two more paradigms, which is shared memory and distributed memory. As the name itself says, shared memory allows multiple processes within the same computer to access a common region or maybe a physical memory, simplifying the inter-process communication um, by treating it like a single memory space. You got me right? So it's just a shared memory where every individual process is trying to access the same data. Somehow we do have some pros and cons for this shared memory. We will just check that in the upcoming slides or upcoming wording. So we do have some this is one of the model for parallel programming. And when we talk about the other model, it's just vice versa, opposite of it. So it's a distributed memory where it involves physically separated memory modules on different computers in a system, require explicit communication, typically maybe via the message passing or distributed shared memory abstraction. That will it just like opposite of what we have spoke about in shared memory. So the concept, when I talk about distributed memory, I'll just give a quick example of what I do on a daily life, how it is related. So as I was saying, let's say I have a single database which is sitting in consider Russia, but I'm a user because I'm talking about the European region. So maybe I'm a user in Germany. I wanted to access the data from Russia, so I have to pass through multiple protocols and security measures and do a communication, fetch the data. So there may be a lot of latency between data fetching. Instead of, that is the shared memory concept which I was talking about. Let's say if I wanted to make it literally better, so what I would do is maybe any guess for distributed memory? Any guess on a distributed memory? I don't see any questions posted or any hands raised. I would think your the session was delivered correct, and you're grasping it. As I said, like let's try to make it little interactive when you wish. But if not, then other way also I can go on. You can also post your messages in the chat. Good. Anyways, um, so the vice versa of this shared memory example, which I just told you, what I will do is as soon as my local database, not local database, I would say, my main database is in Russia, but I'm a user in Germany, as well as I'm a user in consider Poland or Czech Republic, where the user wish to fetch this data before he start running the program. That's the virtual data. It's not the actual data. It's always a virtual data. there will be a copy of data which will be shared with them. It's kind of virtual database, I would say, given to the software. It will fetch the data and then keep it in his own local cache, which will be helpful for faster access. But again, it has also some disadvantages, like, as you know, if any of the one data is been updated on the main database, it may not be immediately reflecting here. Even for that also, we have some methodologies which would work on to synchronize the data in the main database. Okay, so this is just abstracts about what are the different programming models that we have, how they work together. Okay, one is the shared memory and the other one is the distributed memory. Anyways, it will introduce one more model in the upcoming slides. Just quickly go through it. Okay, let's check what does shared memory he's talking about. So as I was talking, as the name itself says, it's a shared memory. All the programs are centrally lying on the central database or central system or central data, which have latencies. Sometimes um, it may have to wait. Just take an example. I hope you might be working on for sure Excel, the basic Excels that what we work on a daily basis, and consider if it is shared Excel between you and other department in the Excel. So as soon as you get into the Excel, you can see two people are working on a same cell. Consider same sheet, same data sheet. You're trying to update a cell where isn't other user also trying to update the same cell. Excel may not be able to take that because you are accessing the same data from different programs and different systems. It definitely have an issue in either updation of shared memory. The the cons of shared memory in, and which will have always an updated data, but there will be a latency in data accessing, which will be really worst when we run a real world applications. You got me? So in shared memory, how does it work? Just like all processing units can access a single and a shared address space. In analog, a team collaborates on a single whiteboard. Consider everyone can see what they are modifying. As I said, like the consider it as an Excel where you are writing in at the same time the other users are able to see what you are typing in and what you are changing it. It is data changes, and same data is being instantly shared across everybody. But still it has some communication problems. Like when you are locking that particular cell for update, at the same time if other program is trying to do that, it should wait on a queue either to let you finish or interrupt your processing. So which might be a issue. um, you know consider in case of banking. Consider in case of banking, you're trying to update through one program on one account. At the same time you're trying to withdraw some amount from a different machine, whereas one definitely has to wait for the others. So where we have a latency on your operation, so you may have to wait for a couple of seconds before you process your request. So that might happen. That's a very basic blunt example which I would say. And also which will have some synchronization problems like logs. As we were just talking about basic example of an Excel, when you try to update something, which will definitely have an issue in giving access to the others. and also some synchronization problems. I mean, I'm talking very plain wordings of what a shared memory can do, or can work on shared memory parallel programming. But when we talk about actual programming models, so we have something called OpenMP, which is a shared memory programming, I would say, methodology, which can help us in understanding and do our programming with shared memory parallel programming. Make a note of it. I try to give some URL, maybe YouTube video tutorial, which will help you in understanding what is open or shared memory and what is a distributed memory, and what are the tools that are used, or that can methodology that can help us in achieving that. Okay, maybe I can quickly type in one of the program which can be executed in C with the OpenMP. I'll just try to ping in here chat. So if you see here, we are including omp.h, which is the shared memory or OpenMP library, with which we can also get how many threads are actually processing or taking to run this program, this particular program which we are executing, which will just give you the threads number. The threads number count will be less here. The reason is we are trying to access a shared memory, and also the execution time will be little lower, means like slower. Okay, you got me? You with me? I hope so. Good. I will go on to a next one, the next model, which is distributed memory. It's just like spread minds or separate minds, but they are coordinating with each other and do the activity as it could. Okay, um, just think, imagine you need to sum a very large array, distribute across the separate memories. How would you combine the results? It's distributed across. Consider 4 or 5 people are working together to sum up a large array in distributed. I mean, like I gave you some values to X person, I gave some values to Y person, I gave some values to Z person, and I want them to sum up everything together, and I need a some I mean at the end one solution. So X will be working on individual, Y will be working on individual, Z will be working on individual, and there should be another processing model which will be collecting all this data and then save it to a readable format, or keep it in for accessibility. I mean, the result should be accessible. So here comes the distributed memory models. So as I was also saying, so it's a virtual memory spread across. There is no shared address space. Instead, they will have their own private memory. In other words, if I have to say, let's say we are thinking about one college database. Yeah, it's not consider it's not shared. And if you wanted to, we can articulate it. I'm trying to get some sensible examples for us to understand this. Yeah, so yeah, true. So our college database is one of the distributed. I mean, it's a shared database across all. So we will have issues in accessing sometimes the same information, because the same example what we have spoke in the previous model. Instead of that, what I would do is, let's say computer science department is trying to access one record. At the same time, accounts department is trying to access the same information. So to be frank, for both of them, the activities are different. Accounts department will be looking at their account related information, like fees paid or xyz information, blah blah blah, related to the accounting. But when you talk about computer science department, they don't look at the account section. They simply look at their curriculum or attendance or etc. etc. So in these cases, we can give the same database, a virtual copy of the main college database, to account system, one copy, as well as to the computer science department, one more copy, where they can work on their own individual information and they can process it at the end, maybe at the end before the college closes. We do bring the data together and merge it to the main database, with which, as we see analogy, a team of people on a separated rooms communicating explicitly via the text messages or email, blah 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 blah. I mean, in our case, we don't really communicate in accessing the information, but still, as you are accessing the same data, we are trying to send the messages at the real time. We would say API calls to the main database and update it at the same time. The information from accounting system also can do the updates, which will be explicitly done through messaging or messages, and which will be an you know yeah I mean feasible solution, one of the feasible solutions in parallel programming models. Okay, here in this distributed memory parallel programming models, communication takes the primary role, and which will be explicitly working on message passing, send or receive operations, and also at the end synchronization. It's achieved through the processes, it also is achieved through messaging, and it sometimes it also has disadvantages. As you already know, every model has pros and cons. Even distributed memory models also can have some issues in processing the data, or making the program work or software work better because of this message synchronization. At times there might be a lag, or consider I have sent an update to the main database, but that message was lost. It could be something, it could be anything, but the message lost, and but your update did not went in, and which is a loss of data. Could happen. So this is also one of the disadvantage, as well as it's also a send and receive operations. There might be some delays in taking out your processing or data processing. Yeah, fair enough. I hope so. Let's move on. I'm just pinging one of the tutorial for OpenMP, and distributed memory models can be worked out better with the help of MPI, message processing integrator or something. It will be said, so which will give more information on distributed models as well as on shared models on programming wise. You can go through this for your future learnings, might be helpful. Just give me a minute. I will try to ping you guys in the chat. Where I can see the chat. Yeah. So this is one of the YouTube tutorial which can help you in identify or understanding the shared memory as well as the distributed memory programming models. Okay, good, great, thank you. Then let's quickly move on. Okay, what is this? We just spoke about only two models in the very beginning. We just said hybrid models and shared models and distributed models. But where comes this distributed shared memory, which is like a hybrid? As we know, every model has its pros and cons, which we would like to bring. Which we would like to get a better model. Now, as I was saying, we are always talking about betterment or improvisation of the existing models, but it doesn't mean that the individual models are not useful or not performing well. Every individual model has its own pros and cons and can be used based on your need. Anyways, that we will see which model can be picked up in upcoming in maybe in a couple of minutes. So I mean, when we talk about hybrid parallel programming models, which combines the programming models, such as we were talking about two programming models in the past, one MP and MPI, which will uh, get the hierarchical hardware architecture, which will work with a high performance computing and bring in the power of both shared memory as well as distributed memory programming models into one model, which is a hybrid model, which is namely distributed shared memory models. Yeah, how does it work? It brings the uh, features from distributed model via message passing, and also get the power of shared memory parallelism from OpenMP or shared memory models, get the benefits of reducing the memory consumption, improved load balancing, better communication efficiency, increase the parallelism. So these are all the, I mean, as I was saying, like every individual model has its own disadvantages. We just wanted to make one model's cons as another model's pros and make one distributed shared memory model. Got me? As I was saying, every individual model has its own disadvantages. I mean, it do has advantages of taking both the shared memory and distributed memory processing pros into one model, but still it has some challenges, like it has some overheads, also some complexity involved in coding, and also sometimes load balancing is not properly done, because one model is trying to overcome with another model's issues. Both will conflict at the end. Might be, it's not that, but it's just one of the challenge. So we might have load imbalance as well as false sharing. It may lead in dropping the messages in between, or some cache problems it might come, which might be issues with distributed shared memory models. Okay, hope we are still in. Thank you for bearing with me in the evening of your time. Try to grab a cup of tea or a coffee, and then try to take this information processed. Anyways, let's move on. I mean, we're all, until now we are all talking about processing models and how does it work, and parallel programming models, how does it work, how it has a problem, why it can be made better, and blah blah blah. In between, there are, I mean, with the advancements in programming, this GPUs and data parallelism has come up. GPUs are, so they are used for parallel computing, a technique where a complete model is replicated across multiple GPUs, each processing a different subset of data, which ensures the parallelism. This parallel processing of data on different GPUs is significantly reduce the time needed to take the processing the data. And also, as we know, right now we are in the world of AI and ML. So this machine learning came up together on its own, train the deep learning models with the large data sets and make the computations literally fast as best as it can. So that is where GPUs came in. As you know, NVIDIA GPUs, OpenCL GPUs are the leading GPUs in the market, which are literally working together with robotics. Yeah, I mean, how does a parallelism works with GPUs? Model replication means the entire deep learning model is copied to each available GPUs, and works within that GPU to provide the information out to the required program. Also, data distribution. The training dataset is split into small batches. So each GPU assigned to do an individual unique task or unique batch of data. I mean, individual tasks for that particular activity, the final activity. At the end, you definitely don't identify what's happening on the backend systems, but still, you should be in a position to see your results are faster enough and accurate enough. And also, it makes the I mean, each GPU independently processes its assigned batch on his data copy and produces an output and give the output to the main program. That is how the data independently processed. You're still there, I hope. Good. So the benefits of using data parallelism with GPUs are like fast I mean fast trainings. Like data will be taken into the individual GPUs and it will have its own learning on that particular set of data, and it can release or it can give you the results in fraction of seconds or maybe microseconds, I would say. Also the scalability. When we talk about scalability, the effectiveness of data parallelism scales with the number of available GPUs. It means like you don't need to really work on, let's say, if I have in my programming models, I've used 100 GPUs. It doesn't mean that all 100 GPUs has to work at a time. Instead, based on your request, the individual GPUs will work and just respond. That's it. So where you are saving a lot of CPUs, I mean GPUs, also power and everything else. Okay, and it has a high throughput because you're working on a distributed workload model. So the data parallelism can increase and train the throughput compared to the single device training. Again, at any point of time, every model has its own pros and cons kind of thing. So even we have to consider, when we are talking about GPUs processing, we have to consider below key points, which are like communication overheads and model size. Where in communication overhead, it's the common issue across everywhere, because as we are working on a distributed computation, the messages processing or the message between one GPU to the other GPU may get delayed or may get lost, and which might increase in communication bottlenecks. As you are increasing your GPUs, the communication bottleneck might be more, because you still have to distribute your query to a specific GPU, whereas uh, on the same GPU, the another processing is still another request is already in progress. It has to still wait. So we have a bottleneck over there. And also the cost of maintaining these GPUs is not that easy. It's really high. Yeah, you can look at NVIDIA's share value. That helps us in identifying how much a GPU can be. It's really high, and that's also one of the limitations to consider this GPU models, or I would say massive parallelism with GPUs and data parallelism. On the same side, we have this PGAs on top of GPUs. We went on PGAs, which is called partition global address space, which is also one of the parallel programming model that provides a global shared memory abstractions for distributed memory systems. If I have to talk about one example, I couldn't really try to fetch an example. Yeah, I couldn't able to really articulate one example for you on this topic on local, I mean, PGAs. But in general, PGAs are also, I mean, it works mainly on below concepts like global address spaces, partition memory, local versus remote data, as well as one-sided communication. So, I mean, as we have seen in the previous model, it has two-sided communication with individual GPUs, and which might bring up in what do you call communication lag or bottlenecks. So with these models, the unlike the traditional two-sided messaging passing, it takes the processing on the top, with the requests on the top, it start pushing it down to the individual processes and do a required matching on the array of already existing data sets or the solutions, and try to retrieve that only information, not that it processes something, but instead it just gives the response on that particular issue or kind of question immediately based on the existing prepared models. So it will not process on that time. Instead, it takes all your data and start preparing the models on its own and give the answers in a single shot. So it means it doesn't make any processing. Instead, it just only looks into the existing models and start giving you the information. And also, as we are talking about local and remote data sets, so accessing the local data is much faster than accessing the remote data, so which incurs the lower communication costs. And also partition memory. So as we know, the global address space is logically divided into partitioning, like few are spread across local, few are spread across remote, kind of hybrid. With each processes are having its own local memory partition, so that it can try to fetch the information based on the request what it has been getting it. Okay, so the main benefits is like productivity increases, obviously performance, asynchronous operations, like as I said, as we were talking about only one-sided communication, so which will not have any what do you call lag or latency in your resolving your requests. And some of the PGA language models are Chapel, UPC++, CoArray, Fortran, blah blah blah. So you can just go through. I mean, even OpenMP, like OpenMP, it also has Open SHMEM, which is also one of the large programming models, PGA language models. These are the advancements which are there in parallel programming models. Yeah, which is industry proven, working better. Also, right now we are working on AI/ML use cases where all these PGAs and GPUs processing is being used to resolve the issues or resolve your queries and give you an answer to that program. Anyways, we have seen multiple models now: GPUs, PGAs, shared memory, distributed memory, as well as hybrid models. But which one you wish to pick it up? I mean, it's not that our wish, but instead we do have parameters. It's just like a flow chart. Consider which model I have to pick up. How is your data parallelism? Whether it is a data intensive problem, yes or no. Accordingly, how many models you need. I mean, how many cores you need, how many machines you need, how much cost you have. Accordingly, the it just like think on you wanted to execute if else block, how it can be done. The same way, when you wish to when you wanted to develop any parallel programming models, you need to think about multiple factors like data, communication, latency, costs, resources, software costs, licensing, security, everything else. All these come into the picture while you consider which model you have to pick it up. Okay. So let's look at the last topic, like last point, like match to parallelism types. So whether you wanted to have a data parallelism, task parallelism, or pipeline, how you wanted to pick up or choose your models. Maybe some of the models may be easily worked on OpenMP or shared memory, but some is better working on message passing interfaces like MPIs. So it all depends on all these factors to choose which model I can pick up to work on my software. Okay, I'll not take too much of time. I think um, get to an end, I would say. If you have any questions, you can post your questions right away here. If it can be answered right away, I will try to answer you immediately. If not, as I was mentioning, I can take these questions from organizers and try to get your answers posted to you back. But yeah, on an abstract, the programming models are different. It all depends on how you choose based on the situation or based on the needs that what we have. I can take any question. You can write or you can speak. I'm fine with it. Anything you can come up with. Maybe a generic question, not only on parallel programming models, but any generic questions that you wish to have from industry standards right now out there, or yeah, whichever of my knowledge, I'm happy to help you with. Hello. Yeah, maybe no. As I see no questions, shall I take it as good, good informative session, or maybe as nothing was understood, maybe a bad session? I don't know, but I would definitely think that you might have got some information sitting with me for this some minutes, and hope this session is little useful for you in upcoming days for your career. As I said, thank you so much. Thanks for having me here. And also, I would like to, say thanks to PBC College of Arts and Science for giving me this opportunity and to bring myself in front of you to, talk about this model together. So let's build a more concurrent future together. I would say thank you so much. Here I would end my presentation, and yeah, I give it back to organizers.
I extend my sincere gratitude to our distinguished speaker, Mr. Sivakishore, for delivering such an enlightening session on parallel programming models. We gained valuable insights on the shift from sequential to parallel computing, the challenges of concurrency, and the different programming models like shared memory, distributed memory, and hybrid approaches. The discussion on massive parallelism with GPUs and data parallelism was impactful. Thank you, sir, for your valuable insights. Thank you so much.
Thank you so much, madam. Thank you so much. I would say have a nice evening. And yeah, you can reach out to the organizers if you have any questions. I'm happy to help you on your questions. In other ways, thank you so much. Have a nice evening, I would say. Thank you. Then we'll drop off. Have a nice time. Cheers.